Problem number 18. A spring of a relaxed length L1 and a spring constant K1 is placed in parallel with the spring of a relaxed length L2 and the spring constant K2. A force F is applied to each end. The combination of the springs acts like a single spring with the spring constant K and the relaxed length L, where we have next expressions for K and L. Solution for problem 18. To solve this problem, we just need to write equation for force. From one hand, this force equal combined force from both strings, which is this expression, and from other hand we have this force must be equal to regular force from combined springs with the constant K and the relaxed length L, which is this expression. Now, from this equation, we can find what is K and what is L. We just need to equalize coefficients for polynomial with the x and the other free member with the zero power. From here we can find that the coefficient K just equal K1 plus K2, and the free member give us this expression. It means that now we can find what is relaxed length L. That will be this expression. It means that the answer is this one, which is answer B, and that was a solution for problem number 18. Problem number 19. In an experiment to determine the speed of sound, a student measured the distance that a sound wave traveled to be 75 plus minus 2.0 centimeters, and found the time it took the sound wave to travel this distance to be 2.15 plus minus 0.10 milliseconds. Assume the uncertainties are Gaussian. The computed speed of a sound should be recorded as following. Solution for problem number 19. In this solution we use fractional uncertainties. Since speed equal distance over time, we add the fractional uncertainties of the measured quantities in quadrature, given next expression. dv over v equal this expression, which is 0.054, and speed equal 75 centimeters over 2.15 milliseconds, which is 349 meters per second. And now we can count what is a dv. That will be 19 meters per second. And the final answer is 349 plus minus 19 meters per second, which is answer E. That was a solution for problem number 19. Problem number 20. A massive uniform flexible string of length L placed on a horizontal table of length L over 3 that has a coefficient of friction mu static equal 1 over 7. So equal length L over 3 of a string hang freely from both sides of the table. The string passes over the edges of the table on smooth, frictionless, curved surfaces. Now suppose that one of the hanging ends of the string is pulled a distance x downward, then released at rest. Neither end of the string ever touches the ground in this problem. The maximum value of x, so that the string does not slip off of the table, is next one. Solution for problem number 20. First, let's write equation for force of friction. Force of friction equal mu static multiplied by mass of part of this string, which is on the table, mass of whole string divided by 3, And if one end of this string is released by distance x from one end, we have equation that force of friction minus x over L mg equal x over L mg. And finally we have this expression to find what is x, and x equal L over 42, which is answer A, and that was the solution for problem number 20.